can continue our discussion. And before we start our lesson, let's pray together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min du'atin la yustajabu laha. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul hazna idza syi'ta sahla. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. All right. And then in the past meeting, we already discussing about problem H and J, and I have added some problem. That is, there are 3 new problems. And then before we continue to the next problem, is there any difficulties about problem J or problem H? Is there any question? All right. And then is there any question about the material? If you understand about dynamic segmentary and persistent segmentary. Oh, sorry, I think the contest already ended. There is the implementation of problem J, right? All right. The proper idea of persistent segmentary. Okay, then before we discuss the next 3 problems, we have to we have to discuss more intense about persistent segmentary, since the problems solved by persistent segmentary. So in the persistent segmentary, the difference is just when we do an update, and the update is just point update, not range update. But here, every time we update the point, we still need to store the previous value. So we cannot modify directly, but we have to create a new node, a new value here. All right. Then what is the example of the problem? Maybe we can try to see problem L. If you read this problem, generally, the problem is just like this. There are some query and update, but there is another operation that is we want to we want to undo some update so that we are in just like in after applying get operation. So for example, there is an initial state and then we update to the next state and then update again and then update again. And then after that, we do fourth operation, which is we want to undo some operation such that we come back into a specific state. That means we have to store each version, right? Since we need to refer to some version. All right. You got it? Did you understand about the fourth operation? All right. And then, so if we remove the fourth operation, can we solve it in just using a simple segment tree? How to solve it? What we store in segment tree, and then how to do the operation to try to find the idea to solve this problem if there is no last operation, last type of operation. There are just three types of operations. Yes, of course. That's it. I think you have got the idea. The segment tree storing what? What we can store in segment tree. We can check the problem. There are n cells and m position for each cell. So we can imagine the bookcase is like this, like this. There are n cells, and then each cells there are m positions. So just like this. Yes, store the number of one. And then how to store a metric into segment tree? Do you know how? This is just like a metric, right? Two-dimensional array. Then how to build segment tree from this? Building segment tree for itself. All right, then how to know the total number of book? How to query the total number of book? Because each update we have to print the number of books. All right, then what is the maximum number of cells? Maximum number of cells is n. So there are so is that means we have to query n times. So if we query n times, the worst case of n is 1,000, and the worst case of q 100,000. Then the complexity will be q times n times log m, since we need to query segment tree, right? Do you have another opinion? And of course, this is greater than 10 to the power of 8, right? That's it. We don't need to create n segment tree, but we just need one segment tree, which is covering 1 until n times m. Let's say 1 until m means this is the first self. After that, m plus 1 until 2n is the second self, and so on. So the total size will be n times m, and the worst case is just 1,000,000. Right. Then Rabiullah has another idea, I think. What do you mean? Sec current 1 and current 2? What is the data type of that variable? Dimensional segmentary. All right. Yes, but we but there is another way that is simpler, which is we can just make it one dimensional, since in the query we don't need to query a specific subgrid, right? We just need to update a specific point or revert a specific cell. All right. Then if we make it just one dimensional, we can also do all of the type of operation. We can just changing a point or updating range, right? Or we also can do like this. We we have segment tree. Sorry, we have m segment tree, and then each segment tree we have the value and become the other segment tree. All right. So we have some small segment trees, and then one big segment tree to store the sum of itself. All right. We also can do this. And then, okay, before we continue to the last type of query or last type of operation, did you understand the idea to solve the other operations? All right. Then, because we because there is a fourth operation which is we undo some update, so we still need to store every version about every version of bookself. Why? Because sometimes we refer to the previous version. For example, 5 reverting from 2. So this is equal to the second version. Back to the second version. After that, we update, become the next version. And then sometimes we revert again to the fourth version, for example. So we still need to store this version, right? Because we will undo this. All right, then we need to build a persistent segment tree, right? In order to store all of the version. But when we store all of the version, since the memory size of segment tree is ON, is linear, and we need to store Q version, Q segment tree, right? Then if we storing all of them one by one, then the memory will be exceed the limit, right? So we have to optimize this. We don't need to store all of the version, but but we need to store the node that is the value is changing. So actually, if we update a specific point, for example, there is a segment tree like this, and then we need to update this point, for example. Then the changing node is just here, and the other is not changing, right? This is not changing. This is also, and so on. So we don't need to create another memory to store on this because this is not changing. So we don't need to create the whole segment tree using the new memory, but we just need to create the node that is changing. For the other node, we can use the same node as this. So this node and this node is in the same memory address, in the same memory, and of course with the same value. All right, we don't need to create another memory here. And the same thing we can use here. So the value is still same. All right. And after that, yeah, if we want to update another value, please don't change the value, but we need to create the new nodes. Why? Because if we change the value directly, then that means we also changing this, right? And we don't need that. All right. How about the third operation? About the third operation, actually we can do this. We can do lazy propagation in persistent segment tree. So how to do that? We can start like this for each node. We need to start the number of one, right? The number of books. And then we need to start the boolean of, is this inverted? Okay, is this inverted? All right. And then we need to start the left child and the right child. All right. If this is not inverted, okay, that means we can directly go to the left child and the right child. But if this is inverted, if this is true, so we cannot visit directly to the children. But we need to create another node, which is the inversion of this. So this will be R minus L plus 1 minus CNT of this. And then the inverse is also true. All right. And so is this. After we create the new nodes, we can change the child become this and then can make it false. All right. So when we try to visit again, then we just need to, we don't need to create the new nodes, but we just want to visit the other, sorry, we can directly visit the children. All right. And after that, for example, there is a node that is still have to be inverted. This is true. And then after that, we want to update to the next operation. Then we will copy this, right? This is not a problem. Even we want to update here in this cells. So this is not a problem. If we want to access the children or go to the children, then we will create the child, right? And then we push the lazy propagation here. So here we also push the inversion to the children as well, because all of them has the same, all of them have the same address, right? So when we change this is also changing. But this is not a problem because this is the same address, so the complexity will be just O1 because this is only the same memory. And then we actually do not changing this. We only complete the update here, right? We do the lazy update the because here we still pending the update, right? We are no need to update now, but sometimes we need to update it. All right. And then the number of visited node will be just logarithmic m, right? So we only create the new nodes when we need to visit that. Right. Till this point, is there any question? Is it understood? Right. So this is the solution. How to do all the operations. All right. Just I already increased the duration, so just reload the page. Okay. So if we want to do the segment tree here, to the persistent segment tree, we have to do this. For example, all right, you have a difficulty about pointer. All right, maybe I have to explain the syntax of pointer. This is left and right is a pointer, not a value. And this is just pointing an address. So the memory is not big since this is only address. If we create a pointer, the memory is just 8 byte and not storing the whole data since this is only address and then pointing some value. All right. Yes, occupy extra memory, but only 8 byte. For example, we have a vector of integer, which is the memory is for megabyte, for example. And then we also have the pointer of vector pointing this. So the value will be the same. We can access some specific memory, sorry, specific value or specific index. We can change it. If we change the value, then this is also changing, right? But this is not storing another 4 megabyte, but only 8 byte. All right. Just same as long long. The address memory is just same as long long. While the integer is 4 byte and the long long is 8 byte. And the memory address also 8 byte. And then when we declare here, sometimes the basic value is 0. 0 means doesn't point anything. All right. So when we build the node starting from the root, the left child and right child is still pointing null or 0. So we have to create a new tree first. We create a new node, then build here and build here. When we build here, we will create the other address. All right. We need to declare right in. All right. Good question. Because here we only declare a pointer, right? But the initial value is 0. All right. Because the initial value is 0, this is not pointing anything, not pointing any nodes. So if we build directly, then we build a null node, then will be runtime error if we don't do this. Because this is still not pointing anything. And we cannot do anything in nothing. We cannot do anything in non-variable. So we have to create a variable, right? So initially we only have one variable, let's say, and then we need to create another variable, right? Or another node. And then we have to create the right node as well, and then we have to create the other descendant and so on. So if initially 0, we cannot build directly. So we have to create the new node first. All right, you got it? That's it. Why we use pointer here? Why not a value, directly a value? Because if we create a value directly, then the graph will be infinity graph, right? We have a node, every node has two nodes, every node has two nodes, and so on. Then this is even cannot be compiled. This is compile error if we make it a value. But if we make it a pointer, this is not compile error because this is initially 0, not pointing anything. Doesn't point anything, and then we have to create another node in order to point something. After that, after we create the new node, we can build here and then create the other node and then build here and so on. All right. And for the leaf, we don't care about the left child and right child. And of course, we don't need to build the new node because this is leaf. We don't care if this is pointing null or 0, not pointing any nodes. All right. After that, since this is not a native variable, this is a pointer. So we don't use dot function, but we changing dot. We use an arrow instead of dot. So if there is a node, we will use dot here, right? For example, this is A. But if this is pointer, then we don't use dot function, but arrow function. All right, this is the difference. Right. Because sorry, this is P. Because actually P is not 3, right? This is just a pointer. This is not 3. So we need to find the node that is pointed by P and then do query here. All right. Is it understood? From the arrow function. And also about update. For the persistent segment tree, in the when we update the value, we are not changing the value directly, but we will create a new nodes. That is the version after we update the value. So we have to return the address of this version. Okay. So if we update this version, become the new version, then we will return the new version. If this is changing. But if there is no change between the previous version and the second version, so we can directly, okay, this means the pointer of this node. So for the dot function, we do form specific node, right? For example, we do update in this node. For example, we do a dot update. That means we do update in node A, right? So this means the address of A. Okay, you got it? And then because if the range is not intersect, because the range is not intersect, so the value doesn't change. So we don't need to create the new node, right? Since the value doesn't change. So we can just return the same address because this is not changing, the value is not changing. But if the value is changing, for example, here the index x is inside the range, so we have to create the new node. Please don't change the value here, but we need to create a new node with the new value. All right. So if previously there is already there there is already a node here, we need to create the new node, which is initially the left child is the same, the right child is the same, and then for example the value is the same, just like we copy a variable, but copy a new variable, not not just pointing. So for example, there is a pointer this pointing the node that is we want to do now. And then we create a new pointer. But please don't point this because we want to create another node. So we will create the new tree here. But the value, uh, we want to change the value, right? Actually, we can do this in order to copy all the value. All right. This means the variable pointed by this, and this is the variable pointed by red. So we want to assign this into this, right? B to A. So we will copy all the value to this node. All right, this is also correct. And then if this is a leaf, then just directly change the value and then just return the new node. All right. Let me give you the simpler example. For example, we have a variable a, which is the value is 5, and then the other variable b, the value is 7. And then we have a pointer c, which is pointing a, and then a pointer d, which is pointing b. So c and d pointing different variable, right? So if we do this means a variable pointed by d, which is b, and this is variable pointed by c, which is a. So this line is equal to this. So we want to assign the value of a into b. So b will be equal to 5. All right. And also about this. So like this, there is a variable a and b. The value is 5, the value is 7. And then c, which is pointing address of a, d pointing address of b. Then the changing value is only in p. P is changing, but the a is still same, and c and d also still pointing the same variable. Of course, if we output this, output the value of d, or the value of variable pointed by d, then the value become 5. Why? Because the value of p, the current value of p now is 5, right? Right. You got it? So for this case, this and red pointing the different node, right? And then if we do this, the node that is pointed by red, copying the value from this node, just copying the value. Then the value will be same, but the address is different. Different address like this, but the value is same. Different variable, but the value is same. All right. And red still pointing the new nodes, and this still pointing the previous node, the previous version. All right. And after copying from this, we will change the value. All right. So copying means we copy the value and the left child and the right child. So we create a new variable, new node with the value is same, and then the left child is same and right child is same. So after that we want to update the value, right? The value become the new value, become y, if this is leaf. And this is the new version. That's why we return red. Return the address of the new version. All right. How about the left and right child? If this is leaf, so we don't care about it. But if this is not leaf, we have to update each of them. So this is the previous version of left, right? Previous left. This is previous right. Here, still pointing previous left and previous right. But after that, we want to change this into the new version after we update it. After we update previous left, become the new version, and then we want to store it to the left. All right. So because we want to update it, there will be a new node, new left, and then we want to point this. All right. And if we already update the left, so that means the right doesn't change, right? So right update, return this, still return the right, the previous right. So the right child still the same, still equal to the previous right. And then after we have the new left child and the old right child, then we want to combine the value between the new left and the old right, become the new value. And then we want to return this. All right. Is it understood? Okay. Then because we want to store all of the value, all of the version, so we have to create an array of pointer. We have to create n pointer, the first version, the second version, the third version, and so on. Pointing all the roads, that's it. Pointing all the roads. So version 1 means a pointer that pointing the road of version 1. Only pointing the road, but the road will point the children and so on. After that, if we update the second value, then the second version, then just point the root thing and so on. Why this is pointer, not a variable directly? Because when we update, we want to create a new node, right? So this will be redundant if we have node instead of pointer, and then when we update, we create a new node and then we copy in the value, then this is redundant. We don't need to will to node here, but just storing the pointer that is pointing this. Since all of the node is persistent, which is the value will never changing. If we want to change them, we have to create the new node and then storing the new value. All right. Is there any question for this? Okay. Then for the persistent segment tree, we just can do point update, not range update. Because like this, if you want to do range update, then the number of new node initially just log n, but we still storing the lazy propagation, right? And sometimes we propagate them. And is it okay? What will be the final complexity? Because this is logarithm n, or maybe we still can, but let's try to analyze the complexity. If we combine the lazy propagation and persistent segment tree, the number of new nodes initially logarithmic n. But sometimes when we have to visit some node, we have to create the new value, right? Okay. But the number of visited not only logarithmic n also. So maybe this is still okay. All right. But for this problem, we can optimize like this. Optimize become the segment tree is like this. After in some level, all of the node covering it's not covering one cell. After that, from the cell covering some position. So when we do range update for specific cells, we actually still changing one node, right? One node, and then of course the ancestor will be also updated. and then all the descendant will be created when we have to visit them. But if we don't need to visit them, then no need to build the node. All right. How to make like this? In order to make like this, we can directly make the value of n become 2 to the power of something. So initially, when we input n, m, and q, we can directly change n become 2 to the power of 10. And this is not a problem, right? We imagine the number of cells is greater than n, but we only place book and remove book in the first n cells. And we also just invert the the first n cells. So the other cells will be never changing. And that's not a problem. But because we already make it 2 to the power of 10, then if we spare it into left child and right child and so on, then after the 10th level, before the 10th level, we always divide into the same size, right? And then all of them will be, this is the first self, and then this second self, third self, and so on. And the size is m, right? The size is m, and then we can partition them normally. Even this is not 2 to the power of something, even this is odd number, this is not a problem. The main idea is we want to create all of the cells become one node. Okay, do you have a question? Let's try to solve this. We want to draw query, and initially there is no book, right? Initially there is no book, so we can build it or okay, never mind. We can build the initial version, which is version 0, become new tree, right? Okay, we can use this. Version 0 is a new tree. And then we want to build the new tree with size 1 until maybe, okay, not a problem. Or we can make it from 0 until n times m minus 1, 0 indexed. All of them is correct. Yeah, but I prefer use 0 here somehow. And then we want to do query. initially we use the previous version, and then if you want to do the first type of update, you have to share the link, and maybe you already have the link. Okay, for the first type of query, we want to input to variable that is int. All right, we want to update. Where we have to update x times m, right? X times m minus 1 maybe. Or if we want to avoid minus 1 here, we can start from m plus 1. So the first cell and the first position. And of course until, but I think this is not equal. Let's start from 0. And we have to make it 0 base. Yes, we considering the metric become a linear array. So index 1 until m or 0 until m minus 1 is the first cells. And then the next m position will be, the next position is the second self, and so on. So here we want to change the x self and y position. All right. And then, sorry, place the book. So we want to change it become 1, right? And for the second operation, we have to change become 0. And for the third one, we want to change update become, sorry, starting from x times m until x plus 1 times m, right? Or we can also make it from x minus 1 times m until x times m minus 1, actually. All right, this is how to update it. And then if you want to do query, sorry, the last type of operation, we want to make the version become the egg version. Yes, after applying some operation. Version 0 means after applying 0 operation, right? And then version 1 means after applying one operation and so on. So after applying X operation means version X. So just point to the same node. Just store the address of the previous version. Alright. And then for each update we have to output the number of books. So just output the value of the current function. Alright. This is the main program. And of course we have to change the operation, right? We have to declare some variable, and then if we want to build and the value is 0, all right. After that, the value will be also 0 for this case. And then when we want to do query, I think we don't need query in this problem. And then yeah, we can just remove it or just leave it, never call it. And then sometimes we want to point update become y. But if the value is already same, okay, never mind. We can just return this, or we want to create a new node with the same value. That's not a problem since the worst case still the same. The worst case still each time we do an update, we will create logarithmic and nodes. Alright. And then sometimes we need to update or to range update, right? But for this problem, the range is more helpful. We can just do this and then we will end when L equal to X and R equal to Y. This is the node that representing that self, right? So this implementation is only for this type of problem. Not all problem can solve it by this. All right. And then the value is equal to R minus L plus 1. This is in the size of the range. And then minus the previous value, right? And then don't forget to store the lazy variable here. The lazy value is Sorry, this is just Boolean. For this problem, lazy is just Boolean and initially false. For the leaf, we don't care whether false or true. So if there is a query here, but for this problem, we don't need to query. But please, we have to push here before we access the left and right. And also for this, before we continue updating, we have to push. And also for the range update, for this problem, we don't need to push because we only update in the upper segment tree, not until the lower segment tree. So we will never accessing lazy update. Okay, then create file. Create lazy become not lazy. Okay. So if the previous range lazy is false, then become true. So if this is A, this is B, then if we want to access the child, become the inverse of A and the inverse of B. All right. But if this is already lazy equal to 1, or the lazy is true, so this is still pointing A and B, not yet pointing inverse A and inverse B. Because after we do the lazy task here, the value becomes 0, right? So it means we still not doing this yet. So we can directly make it false and just copy the value. All right. And that we don't need push here because this problem is special. And then we can do update the left and right. After that we can update the value. All right. After that, what is the push means? If not lazy, then just do nothing. But if this is lazy, so we have to update the child, right? As it become false, and then the child become the reverse one. So we have to create like this. This is the new left, and then this is the new right. The new left is equal to, yeah, we want to create a new node, right? We don't want to change the value directly. Sorry. We have to create a new node. And the same thing we will do for the new right. And then the value of new left will be the same as the value of left. But the lazy is changing. The lazy is changing, and also the value will be also changing. So n alpha become right minus n left plus 1 minus n alpha. Yes, we want to create more nodes. So previously we already have 2 nodes, and we want to create the new nodes. Why? Why we don't change this directly? Because we need persistent segment tree. We are not allowed to replace the value because we still, yeah, still as the node. Okay. So we will do this. After that, we want to change nr here is equal to right. Okay, is this correct? Am I make a mistake? Sorry, we have to change the left become nl and right become nr. Okay, why not directly create in the left pointer? Because we still need the value pointed by the left pointer, right? So push will override. Push will override the pointer. So we'll be pointing the new node. So previously, you're pointing the wrong node because actually we have to inverse, but the children is not inversed yet. So we have to create the true node, the correct node. We want to create a new node which is the inverse of the previous node. Okay, this is the new node equal to the left and so on. Why we do this again? Not just make it true, because sometimes like this. For example, initially this is already inverse, and then after that we already push it. So this is become 0, this is become 1, and we already push it as well. This becomes 0, and then we want to inverse this. So in the new version, this is 1, right? Become 1. But this is not yet inversed. After that, we want to inverse again. So become, yeah, inverse and then inverse, so become not inversed, right? So if you want to push this become not inverted, and then this is become 1. All right. Okay. I think this is enough. Is there any question? So let's try to invite the sample. Okay. Return this when we create a new tree. And it's not declared. Actually, this is maximum queue, right? One six zero. This is would be 6, right? So let's try to create a debug point all right, and then let's make the max n become, because this is only 2, we can make it like this first. And then we want to do debugging each time we update the version. For the first version, we want to change the index 0, right? For the index 0, the number of book is 1, else the number of books is 0. Okay, this is correct. And after that, we want to inverse the second, which means we want to do range object from m until to m minus 1, from 3 until from t until 5. So this is just the same. And then for 3 become 5. Sorry, this is not 5, but will be 3, right? So there is a bug when we update the value. Become r minus l plus 1 minus value. Okay, is it correct? Sorry, I think this is y. Y less than l or x greater than r. I think this should be 3. Let's check the push value. Y, which one is y? Okay. Okay, let's try to output here. What is the L and R, and then what is the current value? Okay, I think we have to. Does this value changing? Okay, so I think we also have to output this 3 and 5, right? Or maybe we have to make it here. Range 0, 5. Okay, sorry, this is sort not update but range. Actually, in order to avoid this, every time we want to copy some code, try to copy to the upside, not downside. So when we copy this function, so don't paste it here, but please paste to the upper side. So when we forget to edit this, then this will be compile error. So we will directly notice the, oh, is this compile error? This is not compile error. Okay, but if this is not inside the struct, this will be compile error, right? Since we declare the update after that. Sorry. So let's try to do again. All right, now the answer is 4. 1, 4, and 0. Okay, after that, let's try to input the sample, the second sample, and values of max n become 2 to the power of 10. 2, 1, 3, 3, 3, 3. 2, 1, 3, 3, 2, 4. Okay, there is a problem here. Here we want to change the value become y, become 0, right? If there is a bug, then we want to remove All right, I think we have to we have to do. We already push it. Okay, I think okay, sorry. Maybe the debug is for your exercise. There must be update here. But for the general idea, do you got it? Did did you get it? Okay, let's try to push here. Present tense. Okay. Okay. Never mind. Anyway, do you have any question about the solution of problem L? Okay. I think it is understood. Then how about problem K and problem M? For the problem K, there are n warriors. Each of them have some type. And then balance means no more than K warrior. Okay. For each type of warrior, not more than K warrior. Okay. That means if more than K warrior, then we have to erase them. Subset of warrior, so we can erase the complement. And then there are some query which we want to hire only from L to R. Okay. Then how to solve this? And we have to solve it online one by one, not doing offline in the last. Because in order to access the value of L and R, we need the answer of the previous answer. We need the answer of the previous query. Okay. Do you know why the problem setter do this at this regulation? Because the author of this problem don't want us to yes, that's it. Don't want to do it using most algorithm. Don't want to solve it offline, but have to solve one by one. All right. Then how to solve it? initially we can make the n version of army. The first version means there is only one army, and then for the second version there are two army. For the third version there are three army, and so on. And then what can we store in the segmentary? We can store just all of them one for the army that is already inserted, and the other is just zero. Or actually we can also make it one, make it all of them is one. That's it, not more than k. So when we add this new army, then sometimes if the number of army is greater than k, so we have to remove the previous army. Okay, that's it. Remove the first one. After that, if we add the army with the same type, then we will remove the second one, the second army from that type. Okay, and then if there is an army with the same type, and then we want to remove the third army with that type, and so on. Okay, you got it. And then every time there is a query L and R, we can use the R version and just query from L to R. Okay, is it understood? Okay, after that, for the last problem, have you read the problem or you got the idea? Here we want to find the number of pair which the distance is small, and then the broadcasting frequency also small. All right. For this problem, we actually need to create a dynamic segmentary, not persistent segmentary. Dynamic segmentary, but we will create some dynamic segmentary. At first, we have to notice that the value of k is small. So we can do brute force for this. We can try the value of f from f minus k until f plus k. Because k, the maximum of k only 10, then this is relatively small. And then we need to create the segmentary of its frequency. So there are 10 to the power of 4 frequency, sorry, 10 to the power of 4 segmentary. And each segmentary, of course, we have to make it dynamic since we cannot make it 10 to the power of 4 times n, right? And also, this value is so big, right? Value of x is so big. So even just one segmentary, we cannot build all of them. So just make it dynamic. Initially just one node, and then every time we need to update, we create the new node. All right. Yeah. Is it understood? Is there any question? The segment tree just storing the number of radio, and no two radio station has the same coordinate. So we want to update. Actually, we have to update one by one. Okay, storing the number of radio in it. So for that frequency, how many radio of that frequency from L to R? Okay, we just want to count the number of frequency. Sorry, count the number of radio. All right. So it's time. Sorry. So we need to sort the radio from the biggest R to the lowest R. And then we update one by one from the biggest R. So when we try to check a specific radio, we already update all the bigger radius radio, and the lower radius still not updated yet. But because this is minimum, so the minimum will be in this radio, right? Because all the start radio have greater R. What if this radio is paired with the other radio, with the lower radius radio? Then we will count it here. When we count this radio, we will get this pair. So don't worry. So at first we don't care about the smaller radius, since the small radio will count it. Okay, you got it? All right. I think that's all for today. I have to prepare for praying, and you have to prepare for lunch. So yeah, let's end our meeting with praying together. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Ya, wassalamualaikum warahmatullahi wabarakatuh. Have a nice lunch. Okay.